So, hello everyone, my name is Likang. I'm from the University of Alberta at the Alberta School of Business. This is a work done by four, Carleton, Alvin Gobson, who is also my supervisor, Carleton, and me. So basically, it's using a multi-level logistic regression to analyze the hot hand theory in hockey for NHL goaltenders. So before we get started, let me ask you a question. How many of you have heard about the hot hand theory? Wow, almost everyone. Okay, so let's begin with just a brief review. So basically, the hot hand theory is first developed for basketball players, and it's first studied by Twitsky in 1985. So it says that a basketball player who has had a better than average performance within the recent past is tend to have a higher than average probability of scoring with the next shot. So although the fans and NBA players, they believed a lot in that theory, it has never been proved, or it has rarely been proved by scholars, and the results of Twitsky actually suggested the opposite, that a higher than average performance in the past would result in a lower than average probability of scoring with the next shot. And later on, this theory has been extended to other sports like baseball and also hockey. So in our paper, there are two questions to answer. First, we would like to see if there is a strictness. That means a higher than average performance lead to a higher than average performance. That's a strictness. And the opposite, a higher than average performance lead to a lower than average performance. That's also strictness. So we want to test if such a strictness exists for hockey goaltenders. And this answer will be no if all the shots are generated by a series of independent and identically distributed Bernoulli trials. So the second question is, if such a strictness exists, do more successful trials in the past lead to a higher than average or lower than average saving rate on the next shot on goal faced by the same goaltender? So we propose some possible explanations for both cases, that if the goaltender's performance is going to be higher than average, probably because more saves in the past increase the confidence of the goaltender, and meanwhile, if that leads to lower than average performance, it can be caused by the motivation effect. That is, if you have failure several times in the past, it will motivate you and encourages you to make a successful trial on the next shot on goal. So our focus is first to analyze the goaltender's performance within AHL playoffs, and then, how does the saving probability depend on players' recent performance after controlling all the other measurable factors, which are, those factors could be divided into three levels. First is the individual level, simply the different players, they may have different reacts to the most recent performance. And the second level is the game level. When the shot happens, what's the score of the game? Whether the goaltender's team is leading or trailing, or is it tied? And whether the goaltender is playing at home or away ice. And the third level would be the shot level, including the shot origin, where the shot comes from, and the shot type. So our data basically comes from Goska.com and hockeyreference.com. After cleaning, we include first all the shots during 2008 and 2016 playoffs, and please notice that we only include those shot on goals. So if a shot is off goal, it's not in our raw data set. And after cleaning, we have just over 36,000 shots, which could be categorized into 9 different seasons, 90 different goaltenders. And for our analysis, we used a called goaltender year combination of goaltender year groups. So we have in total 216 groups. The size varies from 1 shot within the single group up to 678 shots within the group. And the average size is just over 160. The variables in our regression modeling First, we have the dependent variable, which is y, would be the y value will take 1 if it's a safe, and it will take 0 if it's a go, because we are from the point of view of the goaltenders. So 1 means it's a success, 0 means it's a failure. And then the independent variables x, we add up the number of saves within the most recent 5 shots. This number will be changed later on, but the default setting was 5. And then we scaled it by subtracting the average for each group. And the control variables, which is noted by a vector z, including the home variable. If the goaltender is playing on home ice, it will take the value of 1. And the rebound variable, 1 means it's a rebound shot. A rebound shot is defined by Gaussica, I think, is that if a shot happens within 3 seconds from the same side of the team, then that shot will be defined as a rebound shot. And the strength variable that measures the number of the differences in the number of players on each team on the ice. -2 means the goaltender's team has 2 less players compared to the other one, and +2 means the goaltender's team has 2 more players. The game score, whether the team is leading, trailing, or if it's tied, the shot type, we will say later on, and the shot origin. We have 2 specifications for the shot origin. One is numerical one, consists of angle and distance, and the other one is categorical one, that we divide the zooms on the ice into 3 different parts, named corner, top, and slot. So here are all the 7 types of shots we've included. I believe most of you have exercised hockey before, so I won't give any explanations on those types of shots. And the graph, the image shows here is a tipping shot, I believe. And here's the first shot origin that we use the distance and angle specification. Basically, if a shot goes straight toward the net, then its angle is going to be 0. And if the shot is parallel to the crossbar of the net, then its angle is going to be 90. Unfortunately, we are unable to tell whether the shot comes from left wing or right wing of the ice. And the distance is simply the distance between the central point of the net, of the crossbar of the net and the place where the shot happened. On this graph, we shows how we define the corner, slot, and top part. This definition is actually suggested by a former professional hockey player who used to be a student of my supervisor. And we believe that if a shot happens within the slot area, it should have a higher chance to result in a goal or a failure for the goaltender. Although our main focus is to use the multi-level regression model or partial pooling model, well, those names are interchangeable, we have also tested other models like no pooling model and the complete pooling model. Basically, a no pooling model is that you fit a separate regression line to each of those groups. There's no common part within the slope of our independent variable of focus, and there's no common part within the intercept. And the complete pooling model is quite the opposite, that you fit a single logistic regression line to all the whole data set, which ignores the differences between each group. And the partial pooling model, that's kind of like a mixture that you fit a regression line to the whole data set, but you allow the slope of the independent variable and the intercept to change depending on the groups. Which means for each group, you assume there's a common effect on the slope and the intercept, and you believe that there are some group level differences there. The formulas is showing us on the PowerPoint. As you can see, please note that Z is a vector, and meanwhile X and Y, they're just variables. And the Yij means that goalie I in EOJ made a save on shot K, then Yj would take the value of 1, otherwise it would take the value of 0. And Xij is the number of saves in the most 5 recent shots prior to shot K for goalie I in EOJ. So because they are all logistic regressions, so the result would, after taking the log inverse, you will get the probability of the y equals to 1. So this table shows the result and compares the result from the partial polymodel and the complete polymodel, taking our default setting where we count the most recent 5 shots, use the top slot corner specification for the shot origin, and within the same game case. Within same game means that if, for example, for the first game we omit the first 5 shots because they don't have enough shots prior to those 5 ones. And then for the second game of the same goaltender within the same year, we again omit the first 5 shots, which means we assume that the good performance will not carry out to the second game, even though within the same year. So, interesting from this table is when we look at the slope returned by the complete polymodel and the fixed effect of the partial polymodel and compare them with their standard error, we could see that all the slopes and the fixed effects, that they are quite significant, which is a good thing because that indicates it's very likely that there will be a strictness within the performance of the goaltenders. But however, if we take a look at the random effects, which is the group level differences of the influence of the most recent performance, we can see that the random effects actually changes a lot from one group to the other. It could be take up to positive 0.4 and to negative 0.4. Actually, this means if we ignore the group level differences, which means we use the complete polymodel, then in that case, we take a high risk to lose some information about the strictness of the goaltenders. And similarly, if we compare the results from our partial polymodel and the no-polymodel, again, we need to compare those numbers in blue with their standard errors. You cannot directly compare the slope of the partial polymodel to its standard error. You can only compare the fixed effect of a partial polymodel. Again, they're significant for the partial polymodel, but however, they're not significant for the no polymodels. Please note that Tim Thomas 2011 is the largest group we have had in our data set. That means if you use the no polymodel, which means if you fit a separate logistic regression line to each of the group, even though with the largest group, there's still no enough data to allow you to make a statistically significant conclusion about the strictness and also about the sign of the strictness. And we've also moved from the slot top and corner or shot origin to the numerical shot origin and compare the slopes returned by the partial polymodel with all the other settings stayed the same. You can see that it's very good to see the coefficient remains pretty much the same, which means this change does not affect too much. Another thing we are interested in is to see how the different types of the shots will influence the saving probability. According to this chart, probably a wraparound shot would have will result in the highest probability of save, which means the forward should take the least number of wraparound shots as possible, because very likely the goaltender is going to save that. And meanwhile, the deflected shot is the one that is the hardest to save for a goaltender. The results from the distance and angle specification is pretty much the same compared to the top and slot corner specification. But there's only some differences for the tipping and the deflected shots. We believe that may due to the correlation between the distance and angle and the types of shots. And for the case, well, we listed the saving probability for different number of strengths on the ice. the result is what we expect to see as well. That is, if a goaltender has 2 more players on his team, the saving probability is almost 100%. It's very, very unlikely that you're going to lose a goal if you have 2 more players on the ice. Meanwhile, if you have 2 less players, the saving probability drops a lot to just over 80%. So the coaches need to pay special attention to that case. And the effect of whether the goaltender's team is trailing, leading, or have a tie on the ice is not that obvious, even though the trend is what we expect to see as well. That if the team is trailing, the goaltender has the lowest chance to save a goal, and if the team is leading, has the highest chance to save a goal. But the difference is very small. It's just, I think it's less than 1% differences. So far, we have fit all the models using the setting where we measure the past performance based on the most recent 5 shots, but 5 may not be a good number, so we have computed the case for last 10 and 15 shots, and also we allow the good performance to carry out to the second game, which means we are not restricted to the shots within the same game case. We allow the shots to carry over across different games. That is saying that if a goaltender, for the second game attended by a goaltender within the same year, we do not need to omit the first few shots because they don't have enough prior shots. But in that case, we just keep them. And if you look at this table, there are 2 things to mention. First is, if we move from last 5 shots to last 15 shots, we keep losing observations. That's quite obvious. And the loss of observations is more severe if we move from across different games to within a shot game case. That is, for example, if we take the last 15 shots to measure the most recent performance and use the within the same game case, we have lost about 1/3 of the observations compared to the last 5 shot case. So that may be an issue. Another thing is, as the number of the shots we used increases, the weight of each shot actually decreases. Especially if you look at the slope of within the same game case and compare them. For example, the slope for the last 15 shot case within the same game, that's about 1/3 as large as the slope for the within the same game case and for the last 5 shot case. So the main conclusion for our analysis is first, yes, such a strictness does exist. And secondly, the results suggest that the higher than average performance on the past shots lead actually to a lower than average saving rate on the next shot on goal, which is a little bit surprising. And yeah, like what I said, this may be due to the motivation effect of the goaltenders. So thanks for your time, and this concludes pretty much my talk.
So just on your very last point, I wonder, is that not just a manifestation of regression to the mean? I mean, you perform better than average, you're going to come down.
Yes, okay. So basically, it's possible that you perform better than average, but you come down, but not in that case, because you perform a regression like that. And actually, we have also tried to rearrange the shots. So they are no longer in order, but they return the same result. And also, another thing is, go back to the average that happens in the long term. But you know, there's no data set that is long enough to see that effect. Yeah. Hope that answers your question.
Thank you.
Hi, did you look at any data with regards to game by game as opposed to shot by shot? For instance, you know, a hot goalie gets a shutout, and then the coach has a choice whether to play in the next game or not.
would you mind to specify a little bit more about what do you mean by gaming it by game?
So you know, say a goalie has a shutout, he's hot, he's streaky. You know, then the coach is faced with a choice: do you play that goalie again the next game, or do you play the other goalie on the team?
In that case, then you're expecting to see that if the number of the games played by a goalie increases, there should be also an increase on the strictness of the goaltender's play, right? Like if a goalie is hot, the coaches tends to let the goalie play more games compared to other goalies.
Correct. And I'm asking if the data backs up that decision, whether you know, one game, you know, has any effect. You know, one hot game, you know, is more likely to lead to 2 hot games, to 3 hot games, to 4 hot games, versus, you know, the goalie has to regress to the mean at some point. You know, I guess an extension of that question is if there's any data when that regression to the mean happens or starts to happen, and you know, if a goalie's hot, for how many games should the coach ride it? I know that's a lot of questions, but
that could be a very interesting point to illustrate.
So thanks again. Interesting presentation. I think I'm going to build on the last question from Sam there. I think what Sam's really saying is, can we get 30 or 30 plus shots so that the decision by a coach between games comes into the sort of the model more directly? And then the big picture, I'm an economist, so predicting recessions, right? The longer we go without one, the more likely one's going to come. Goals are scored in games, so the longer we go without a goal, the more likely one's going to come at some point. So I think when you get to the 5 to the 10 shots, it's not quite clear that that's the hot hand. I think people in hockey see hot hand as games over game. So I'm glad you got to the overlapping part, but we'd like to see kind of 30 plus shots in the model. And also with the overlapping, you don't lose your sample size so quickly as well, so it might help on that side as well. Thank you again.
And we have a request for you to put up your results slide again.
This one last one before his name.
Sorry, whatever your last slide was just before the end.
The last slide here.
The conclusion.
Conclusion.
Yeah.
Okay.
Yes, and I didn't have anything else to say.
Any questions?
Hi, thank you for your interesting presentation. I was just wondering if you have data for the timing of the shots, because if you do, then it would be very interesting. Instead of looking at the last 5 shots, you could look at what happened in the last 2 minutes or the last 5 minutes. And I think this may be more informative because performance during a fast-paced game may be different from performance during a slow-paced game. And also, you will eliminate this problem where you don't have any data. You can't use the first 5 shots. So if you look at the last 2 minutes, then if there is no data, it's still data.
Yeah, we do have this kind of data, so yeah, we will do that analysis to see if there's anything interesting.
I might have misunderstood maybe your results, but I was surprised to see that by factoring in sort of the distance and the angle of the shot, those results actually seem to be slightly worse than just looking at the group by category type. So yeah, I was wondering if you had any comments on that, because I think based on the work that we've done, we've noticed that you can build better expected goals models using polar coordinates, like using distance and angle. So yeah, just curious if you had any insights into that.
Okay, so one witness of the distance and angle specification is the relationship is very unlikely to be linear. That depends on the way that you define what the angle and the distance is. For example, a shot that comes from 300 meters away now takes the absolute value of 0 to get to resolving the goal, no matter how likely it is shown according to the regression. And meanwhile, it's very hard to say that a shot has a degree of 90 is more likely to be within the goal compared to the shot has a degree of 75 or something like that. So that may be an explanation to why the distance and angle is not our first choice and may result in a slightly worse result compared to the other specification.
So the follow-up is, are there non-linear approaches to doing this type of work?
Actually, you can. Actually, you can include those, use this distance and angle, but it's going to be a little bit hard to be interpreted. Like you use the distance square instead of distance, or angle square, or distance times angle as your independent variable or as your control variable within your regression model. But the result will be very hard to be interpreted.
I was just wondering if you looked at regular season data, because in the playoffs, generally all players are more streaky, especially goalies. So I was wondering if it'd be more representative by using that data instead of playoffs.
Well, yeah, that's a good question. So we choose the playoffs only because we believe if strictness exists, it's very, well, it should be more clear with the playoffs because the goaltenders, they are going to play with the same team several times during a very short time period. Instead of for the regular season, they are facing different teams match after match. So yeah, if the result does not suggest or suggest a negative correlation between the recent performance, then we are expecting to see almost the same trend, but maybe slightly weaker in the regular season data as well.